Hello everyone, this is lecture 56 of Principle of Electric Circuits. Based on the discussion of the serial RLC second-order circuit in the last lecture, this lecture we will discuss a parallel RLC second-order circuit. This is a ZIR RLC second-order circuit. Because it's parallel, so we need to use KCL on the node. We know that IR equals IL plus IC. In addition to the topological constraints, we also need to apply the elementary constraints of the three components. For the resistor, IR and UC have non-associated reference directions, so we know that UC equals minus R times IR. For the inductor, IL and UC have associated reference directions, so UC equals IL times DIL over dt. For the capacitor, UC and IC have the associated reference directions, so IC equals C times DUC over dt. We can deduce the second-order ODE with any branch variable using these simultaneous four equations. For example, the derived equation with IL is d square IL over dt square plus 1 over RC times DIL over dt plus 1 over LC times IL equals 0. Similar to the previous lecture 55, we can also define this term as 2 alpha, and this term as omega 0 square. So we can get its characteristic equation, that is lambda square plus 2 alpha lambda plus omega 0 square equals 0. The following discussion would be very similar to those in lecture 55, but we won't discuss it. Why? Do you still remember the concept of duality introduced in lecture 46? We said the capacitance and inductance have a dual relationship. Resistance and conductance have the dual relationship. And serial and parallel has a dual relationship. So the RLC serial second-order circuit and the RLC parallel second-order circuit have dual relationship. We might as well write the circuit equations and characteristic equations of these two circuits. For RLC serial circuits, as we discussed in lecture 55, the equation with UC as variable is that d squared UC over dt squared plus R over L times duc over dt plus 1 over LC times UC equals 0. Its characteristic equation is lambda squared plus R over L times lambda plus 1 over LC equals 0. For the RLC parallel circuit in the left, we took IL as variable, and the list its equation is d square IL over dt square plus 1 over RC times DIL over dt plus 1 over LC IL equals 0. Its characteristic equation is that lambda square plus 1 over RC times lambda times plus 1 over LC equals 0. Compare these two equations. We can find that after changing R to G, L to C, and C to L in the right equation, it becomes the same as the left equation. Similarly, if we change R to G, L to C, and C to L in the left equation, it will become the right equation. So this is an important reason why we stopped deriving many conclusions of RLC parallel second-order circuit just now. Because if we skillfully master the four conditions of overdamping, critical damping, underdamping, and no damping for the RLC series second-order circuit, by using the duality theorem, these conditions can be directly mapped to the RLC parallel second-order circuit. You can find that the duality theorem has very profound application in circuits. Well, that's the end of this lecture.